Recently, I participated with my team in the Pentathon CTF and ended up securing the fourth rank. The challenges were very well made, and particularly, I found one pound challenge to be very interesting, so I would like to discuss its solution in this video. Vault is a simple CLI password manager written in C. It's the highest rated 1000 point hard pound challenge, which I believe was only solved by two teams, including my own. So in this challenge, we are provided a Docker file which is used to host the Vault binary on a specific Ubuntu machine. Luckily, we are provided the source code for the challenge, so let's take a look at that first. The program begins by asking for the master password input and displays its MD5 hash. After that, it starts the actual menu driven program to manage the passwords. Let's quickly take a look at how these operations are being performed, starting with the first, which is adding new passwords. The program allows you to store up to 5 passwords at a time. Each time you can specify the URL, username, email, and password, all of which gets immediately encrypted after storage. As far as the actual encryption logic is concerned, the program uses plain old XOR cipher with a random key, so not strong at all. Next, removing a password is as simple as deleting its index, because that's the only check which happens in the list function. Updating is a bit complicated because, first of all, the function is not called regularly. Instead, a new thread is spawned, inside of which the update function gets called. The function requires you to give the old master password, and if it matches, only then you can update the new master password. But even then, only the first character gets updated while the rest remains the same. There is also some sort of blacklisting of characters, possibly to make the challenge harder, but I don't know, it really didn't affect my solution in any way. Anyway, that's not important. What's important is that we have a buffer overflow vulnerability here. Look at this read call. We are reading data from standard input into a variable new underscore buff, which is designed to hold at most 30 bytes. But the size field for the input is determined by the size of another variable with a similar name but much bigger size of 80 bytes. So overall, we have a 50 byte buffer overflow in this function. Keep this in mind as this will be very helpful later. Next, the share function is basically empty and not useful at all. Similarly, the password generator function does what it needs to and nothing suspicious. So before we begin exploiting, I will start by fetching the libc and loader files from the given Docker environment and patch the binary to use those libraries instead of relying on my system. This makes it much easier to test and develop the exploit since it is almost similar to what happens on the remote servers. Anyway, so the buffer overflow is the important vulnerability here. Let's also take a look at what additional protections have been enabled on this binary to see which attack vectors are feasible. You can see that due to NoPy, we have all the absolute addresses from the program, thus we can use gadgets to build a ROP chain. But we can't directly overwrite the saved return pointer because the stack canary is present, which means we would have to leak it first so that when we ROP, we don't clobber the canary and trigger a crash. So let's see how to leak the canary before moving ahead. If you think about it, the buffer overflow vulnerability is in a new thread, and in case of a crash due to overwritten canary, the new thread will crash instead of the main one. So we can still interact with the program as usual. This allows us to brute force the first byte of the canary where all wrong values will lead to a stack smashing detected error. But the one byte which is correct would not trigger this error. This way, by checking whether we receive the error message or not, we can leak the first character. After that, we can simply repeat the process for the rest of the canary and brute force it one byte at a time in a practically feasible way instead of brute forcing all characters at once, which is just impossible. Also, let's test this once before moving on. As you can see, we get a perfect canary leak, which we can verify from GDB by using the canary command of pound debug. So let's focus back on the buffer overflow. With the right canary, we will be able to smash the stack and write a ROP chain. At this point, it is typically game over, but here we are facing a slight issue. You see, the offset for the return pointer is 72, whereas the read only allows us a maximum of 80 bytes. So at max 8 byte ROP chain is allowed, or simply speaking, a one gadget can be executed. And that is not good because this program does not have a magical win function. So we need to somehow find another way to execute our larger ROP chain. One way I think is to store the ROP chain somewhere else and pivot the stack to that location. Because at the end of the day, this is a password storing program and we can easily store the ROP chain in the form of URL, username, email, and password fields of the password block struct and eventually pivot to it. Now, for Actually, pivoting the stack, you would typically need a pop RSP gadget, and while that does exist in the binary, it needs another 8 bytes on the stack to determine where exactly to pivot to. So that's a total of 16 bytes on the stack, whereas we only have 8 bytes at max. So you need to think clever. I will choose a leave instruction here because the way it works is that leave will take whatever value is in RBP and move it into RSP. This pivots the stack, and then the top value from the new stack is popped back into RBP. Basically, if you can get RBP to be target minus 8, then leave will magically take care of the rest. The reason I choose this is because if you look at the registers at the time of return, you will notice that we have full control of RBP without requiring any extra bytes. So this is a perfect candidate for our case. If you test this, you will see that while the pivoting itself works, the ROP chain actually gets corrupted. Because what is happening is that immediately after storage, the program goes on to encrypt all these fields with a random key using the XOR cipher. So we need to fix that first before moving on. If you look closely at how the encryption is taking place, you will notice that in every iteration, the seed for the pseudo random number generator is being reset to a fixed value, then a random number is being generated, which is used for the XOR cipher. But the thing is, if the seed is same in every iteration, then every time we get the same random number. So overall, the strength of the cipher is dependent on how random this seed is. If we can predict the seed, we can break the encryption. And predicting the seed is actually very trivial because just look how it is being initialized. The current timestamp divided by 5. And if you know basic C programming, you know that this is a floor division. And in floor division, the output stays the same for a duration of n, where n is the divisor. Essentially, in our case, for a duration of 5 seconds, we will get the same seed. So if you connect to the remote machine and immediately run a dummy program to simultaneously generate the seed for us, we will be able to get a 100% correct prediction for the key. So let's quickly make a simple script to leak out the encryption key and patch it to use the provided libc for exact function definitions. After that, we can simply grab the key as soon as the IO connection is established. This key can be used later for the XOR cipher before sending the input to neutralize the encryption by the program. As of now, I will be creating a simple puts ROP chain to leak a resolved entry from the global offset table to get a libc leak. Because with libc we have access to much more powerful gadgets that will eventually allow us to spawn a shell. Also, because the XOR encryption is a bit weird in a way that the last character is not being encrypted, so you should not XOR it while sending the payload. So to resolve that, I have created a simple helper function which will give me the formatted payload without worrying about the XOR logic. Anyway, as you can see, we are able to execute our puts ROP chain to get a libc leak. But inside of puts, we encounter a crash. The problem is that due to multiple nested function calls, the RSP moves up significantly. And since we had pivoted our stack to the program's BSS sections, creating these stack frames have gone beyond what this section can accommodate and eventually lands into a non-writable region, creating a segmentation fault. Now, I don't know exactly how to deal with this, so I just choose to create more password entries as this will push our option further down, which hopefully allows us to accommodate those stack frames and get a leak. Let's try it and see the result. As you can see, we have successfully got a libc leak. Now, let's restart the program by calling main and start using this info. But again, we got a crash due to a similar stack issue. And at this point, I really do not know how to fix it. So let's just assume that the program cannot be restarted and take a step back and think, why exactly do we need to restart the program? Well, as I understand it, the purpose of restarting the program is to have another opportunity at exploiting the vulnerability. That is another buffer overflow leading to ROP chain. But this time we will perform a return to system attack to spawn a shell because we have the entire libc at our disposal. So how do we achieve this without restarting the program? Well, we don't necessarily need to restart the program, we just need to find a way to load stage 2 ROP chain into memory and redirect code execution there. Basically, we need a read and return type of gadget. And that seems very rare at first, but if you look at the source code again, you will see this experimental share password function. This is exactly what we want. In fact, if we control RSI via some gadget and jump midway into this function at plus 39 offset, then we will be able to get an arbitrary read primitive. Basically, we can load stage 2 data at any desired memory location, and what's better than the end of stage 1? Because if stage 2 is loaded at the end of stage 1, then immediately after this function returns, we would automatically start executing our stage 2 and pop a shell. However, keep in mind that this function also has a canary check. So your stage 2 should contain a canary somewhere as well. And the corresponding address for that canary should be in RBP. So overall, this part requires some manual fuzzing, which you will have to figure out on your own. But yeah, once that's run, the exploit might look something similar to this, which when you run it, spawns a nice clean shell giving us the flag. So yeah, that's it. Very fun, very interesting challenge. Thoroughly enjoyed it, and I hope you enjoyed the write-up as well.